there are places in the galaxy where morning does not belong to a single sun. On a world moving around two stars, the light would arrive in changing proportions. One star might rise first, followed by a smaller companion. Their paths across the sky would shift as they circled each other, sometimes drawing close, sometimes separating, while the planet continued on a much wider journey around them both. This kind of world is called a circumbinary planet. The word describes the shape of its orbit. Instead of belonging to one star in a double system, the planet travels around the pair as a whole, following the gravity of their shared center of mass. The stars perform their shorter orbit inside. The planet traces a larger ring beyond them. NASA science. For a long time, such an arrangement seemed difficult to imagine as a lasting home for a planet. Two moving stars create a gravitational field that is never perfectly fixed. Too close to the pair, an orbit can be stretched, tilted, or broken apart. A young disk of gas and dust around the stars also stirred by their motion, making the early steps of planet formation more complicated than they are around a single sun. And yet nature found stable paths. The clearest early proof arrived through NASA's Kepler spacecraft. In 2011, astronomers reported Kepler 16b, a planet comparable to Saturn in mass and size. It circles two low-mass stars every 229 days, while the stars complete their own orbit in about 41 days. The three bodies move in nearly the same plane, a clue that the planet likely formed from a disk surrounding both stars rather than being captured later. Adds 2. Kepler did not photograph the planet directly. It watched changes in light. The two stars regularly passed in front of each other, producing deep, predictable eclipses. Then smaller dimmings appeared at times that could not be explained by the stars alone. A third body was crossing first one star and then the other. Because both stars were moving, the transits did not repeat with the simple rhythm expected from a planet crossing a single sun. Their timing shifted. Those variations, once modeled together, revealed the architecture of the entire system. Kepler 16b is a gas giant, so there is no known solid ground on which to watch its twin sunsets. Its importance lies elsewhere. It showed that a planet could survive around two stars, not as a temporary visitor, but as part of an organized system shaped by the same broad processes that build planets throughout the galaxy. NASA science, more examples followed. Kepler 47 revealed that a binary pair could be surrounded by several planets, turning what once looked like a rare celestial arrangement into a genuine kind of planetary system. These worlds are still difficult to find because their transits depend on several moving orbits lining up from our point of view. The ones already known may therefore represent only the small fraction whose geometry happens to reveal them. NASA Science 4. Tonight, the path begins with that shifting geometry. We will move outward from the close dance of two stars, across the unstable inner boundary where planets cannot remain, and into the regions where gravity settles into a repeatable pattern. From there, the question widens. How do planets grow in a disk that is constantly being disturbed? What kinds of seasons can exist beneath two sources of light? And could any such world remain calm enough for long enough to become more than a place of changing sunsets? Far away, two stars continue around each other, and a planet keeps time around them both. The story does not become more complicated because there are two stars, it becomes more rhythmic. Every binary system has an invisible point around which both stars move. Astronomers call it the barycenter, the shared center of mass. It is not an object. Nothing has to occupy it. It is simply the balance point created by the masses of the two stars and the distance between them. When the stars are similar in mass, the barycenter lies somewhere between them, often near the middle. Each star follows its own orbit around that point. Neither one remains fixed while the other circles it. Both are moving, held in a partnership shaped by gravity. When one star is much heavier, the balance point shifts toward it. The smaller star travels along a wider path, while the larger star makes a tighter loop. From far away, the system may appear to contain one nearly stationary sun and one active companion. In reality, both are always responding to the same shared pull. A circumbinary planet travels around this entire arrangement. Its orbit does not center on either star, it centers on the barycenter. Over the course of the planet's longer year, the two stars may complete many smaller circuits within its path. Their individual positions change from day to day, but their combined mass keeps the planet bound to the system as a whole. At a great enough distance, the planet responds almost as though the two stars were a single source of gravity. This is an approximation, but a useful one. From far away, the small separation between the stars matters less than their total mass. Their gravitational effects begin to blend. The planet follows a broad, stable path around the pair, while smaller variations pass through its orbit, like faint ripples. Closer in, those ripples become stronger. The planet no longer feels a smoothly averaged pull. One star approaches while the other retreats. Their combined gravitational field changes direction and strength as they move. Each passing cycle can alter the planet's speed by a small amount, tugging it inward at one moment and outward at another. If the planet lies too near the binary, those repeated tugs do not always cancel. They can build over time. The orbit may become more elongated. Its closest approach may shift. Its plane may tilt. In some cases, the planet can be sent into one of the stars, pushed outward into a distant orbit, or removed from the system completely. Around every close binary, there is therefore an inner region where long-lived planetary orbits are difficult or impossible. The exact size of this unstable zone depends on several things. The separation of the stars matters, so does the shape of their orbit. Two stars moving along nearly circular paths produce a different pattern from a pair following a stretched ellipse. The balance of their masses also changes the way their gravitational influence is distributed. There is no single boundary that applies to every system. As a general pattern, however, a circumbinary planet must remain several times farther from the barycenter than the distance separating the stars. Beyond that threshold, stable paths become possible. Inside it, stars disturb the planet too strongly for the orbit to remain dependable over long periods. The boundary is not a solid wall. A planet cannot see it or cross a visible line. It is a mathematical change in behavior, a place where one kind of motion gives way to another. On one side, small disturbances remain limited. On the other, they can grow until the orbit no longer survives. Near this edge, orbital resonances become important. A resonance occurs when the timing of one orbit forms a simple relationship with another. A planet might complete one circuit while the stars complete several. Their gravitational encounters then occur in a repeating pattern. Some resonances can help organize an orbit, others can steadily disturb. A small pull delivered at nearly the same point again and again may have a larger effect than stronger pulls arriving at random times. You can imagine pushing a swing. The force of each push may be modest, but timing matters. Applied at the right moment, the motion grows. Applied at changing moments, much of the effect is lost. The comparison is not exact because a planetary system moves in 3 dimensions and every body pulls continuously on every other body. But the role of timing is similar. Repetition can turn a small influence into a lasting change. Many of the circumbinary planets discovered by Kepler travel surprisingly close to the inner edge of stability. They are not inside the chaotic region, but several sit only a little beyond it. This pattern has become one of the more interesting clues in the study of these systems. It may partly reflect how the planets formed and moved. A young binary star is surrounded by a disk of gas and dust. The stars clear material from the center of that disk, carving out a broad cavity around themselves. Farther out, matter continues to orbit both stars. A growing planet within the disk can exchange angular momentum with the surrounding gas. These interactions may cause the planet to migrate inward. It moves gradually toward the central cavity until the structure of the disk, the binary's gravity, or a resonance slows its progress. The result may be a planet parked near the boundary, close to the stars but not close enough to be lost. This idea does not explain every system, and the known population is still small. Detection also favors planets with shorter orbital periods, because they cross their stars more often during a telescope's observing window. Worlds farther out take longer to reveal themselves and may never transit from our point of view. The apparent gathering near the inner edge may therefore contain two stories at once. One story belongs to nature. Planets may truly accumulate there after migrating through their birth disks. The other belongs to observation. Those are the planets our instruments are most likely to notice. Separating the two requires more systems, longer observations, and methods that do not depend entirely on transits. Even the stable planets do not follow perfect ellipses in the simple way often shown in diagrams. The two moving stars continually reshape the planet's path. Its orbital period may vary slightly. The direction of its ellipse can rotate over time. The plane of the orbit may slowly precess, changing its orientation relative to Earth. Because of this precession, a circumbinary planet may transit for several years and then stop. The planet is still there. Its orbit has not failed. The alignment has simply changed. From Earth, the planet's path no longer carries it across the face of either star. Centuries later, the transits might return. This gives circumbinary systems a different relationship with visibility. A planet can move in and out of detectability without changing its physical existence. What appears absent may only be hidden by geometry. The stars themselves also create shifting eclipse patterns. Sometimes one passes in front of the other. Sometimes the planet crosses the larger star. On another orbit, it may cross the smaller one. The timing changes because every participant is moving, and each event contains information about the masses, sizes, and positions of the bodies involved. What looks at first like irregularity can become a precise map. By measuring these changing intervals, astronomers can reconstruct the architecture of a system they cannot resolve into separate worlds. Gravity leaves its record in the timing of the light. Far beyond the telescopes watching from our part of the galaxy, the motion continues without confusion. The stars circle their common center. The planet keeps beyond the unstable edge, and through every changing alignment, the system holds its balance. The difficult part begins before a circumbinary planet has an orbit of its own. Long before there is a completed world, there is a disk. Gas and dust surround the young pair of stars in a flattened structure, rotating around their shared center of mass. From a distance, it resembles the kind of protoplanetary disk that can form around a single star. Closer in, however, the motion is less orderly. The stars sweep through the center of the system, raising waves in the gas and pulling material into changing patterns. Their gravity clears a cavity around the binary. The cavity is not empty in the strict sense. Streams of gas can cross it, and some material may still fall inward toward the stars. But the density is much lower than it is farther out. The inner edge of the disk becomes an active boundary, shaped by repeated gravitational forcing. This is where the first problem appears. Planets begin with very small particles. Grains collide and sometimes stick. Larger aggregates grow from dust to pebbles, from pebbles to rocks, and eventually toward bodies large enough for gravity to dominate their development. Around one star, even this process is difficult. Around two, the repeated stirring can make collisions faster and more destructive. Small objects do not all follow exactly the same path. Gas drag affects them according to their size. The binary's changing pull shifts their orbits in different ways. Two bodies that might have approached each other gently in a calmer disk can meet at higher speed. A slow collision may allow material to merge. A fast one may shatter what has already formed. For years, this led some models to suggest that circumbinary planets would have trouble growing. Near the places where many of them are now observed, the environment seemed too disturbed. Planetesimals, the early building blocks of planets, could be broken apart more quickly than they accumulated. Yet the planets exist. That simple fact means the formation story contains another step. One possibility is that the first substantial growth occurs farther from the stars. At greater distances, the binary's direct disturbances are weaker. Relative collision speeds can be lower. Solid material may have more time to gather into durable planetary embryos. Once those embryos become large enough, they can move inward through the disk. A planet embedded in gas does not travel in isolation. it raises spiral waves ahead of and behind it itself. The gravitational exchange between the planet and those waves changes its angular momentum. Depending on the structure of the disk, the planet may migrate toward the center. This movement is gradual compared with a human lifetime, but rapid compared with the age of a planetary system. A forming world can cross a large region of its disk while the gas is still present. As it approaches the cavity carved by the binary, the conditions change. Gas density rises sharply at the cavity's outer edge, creating a pressure structure that can slow or halt inward migration. Resonances with the two stars may also become important. The planet can become trapped near the boundary. This offers us a natural explanation for why several known circumbinary planets lie just outside the region where stable orbits begin. They may not have formed where we find them. Their present positions may be the end of a long inward passage. The journey is not always smooth. The inner edge of a circumbinary disk is often not perfectly circular. Simulations show that it can become eccentric, with its center displaced from the barycenter. It may slowly precess, turning over time, producing arcs, knots, and spiral features. A planet moving through this environment can have its own eccentricity altered. It may exchange energy with the disk, with the stars, and with other planets. In some circumstances, migration stops in a stable configuration. In others, the planet is pushed into a dangerous orbit or scattered away. The systems that survive are the ones we later observe. This creates a quiet selection effect written into the architecture itself. There may have been other worlds during the early stages, worlds that migrated too far inward, collided, or escaped. The present system is not a full record of everything that formed. It is the arrangement that remained after the unstable possibilities were removed. Multiple planets add another layer. In a disk with enough material, several planetary cores may grow at different distances. As they migrate, they can approach one another and become locked in resonance. Their periods may settle into simple ratios, allowing their gravitational interactions to repeat in a structured way. Sometimes this produces a compact, ordered system. Sometimes it leads to instability. A planet can transfer momentum to another, sending one inward and the other outward. A close encounter can increase orbital eccentricity. One world may be ejected, while another remains behind on a wider path. Kepler 47 shows that more than one planet can survive around a binary pair. Its known planets occupy separate orbits around the same two stars, demonstrating that circumbinary systems are not limited to a single fortunate survivor. The existence of such systems changes the question. It is no longer enough to ask whether a planet can endure two stars. We also have to ask whether a complete planetary system can assemble, migrate, and organize itself there. The answer appears to be yes, though not by following exactly the same path as planets around single stars. The composition of these worlds is shaped by where they began. Farther from the central stars, temperatures in the disk are lower. Water and other volatile compounds can freeze onto grains. Solid material becomes more abundant beyond the regions where these substances remain vapor. A planet that forms there may gather a large icy core and then capture a deep envelope of hydrogen and helium. If it later migrates inward, it carries the memory of its colder birthplace. This may help explain why many of the first circumbinary planets found by transit surveys are large worlds, often comparable in scale to Neptune or Saturn. Part of that pattern is observational. Large planets block more starlight and are easier to detect, but formation also favors rapid growth, where solid material collects efficiently. At pressure maxima near the inner disk edge, drifting dust can accumulate. Gas normally causes solid particles to lose angular momentum and spiral inward. A pressure bump can interrupt that drift, allowing material to gather instead of being lost. These dust traps may become important construction zones. They do not guarantee the formation of a planet. Collisions, turbulence, and the binaries forcing remain present, but they can concentrate the raw material enough for growth to continue. Observations of young binary systems support the broader picture that circumbinary disks are real and often structured. Telescopes working at infrared and radio wavelengths can trace warm dust, cold dust, and molecular gas around pairs of young stars. Some disks show central cavities, others reveal rings, asymmetries, or spiral patterns. These images do not show completed planets in most cases. They show the environment from which such planets could emerge. There is a long interval between a patterned disk and a confirmed world. During that interval, gas disperses, collisions reshape the solid bodies, and planetary orbits continue to evolve. By the time the system becomes easier to observe, much of the evidence from its youth has vanished. Astronomers therefore reconstruct the process from different ages. Young binaries reveal disks, mature binaries reveal planets. Computer models connect the two, testing whether a plausible disk can produce the kinds of systems we see. No single model captures every detail. Gas turbulence is difficult to represent. Dust growth spans an enormous range of size. Magnetic fields, radiation, heating, and in chemistry all affect the disk. Even the stars themselves may change their rotation and activity as the system develops. Still, the broad sequence is becoming clearer. A binary pair forms inside a shared cloud. A rotating disk remains around them. The stars open a central cavity. Solid material gathers where growth is possible. Planetary embryos develop, often farther out. Gas interactions move some of them inward. The inner disk edge slows the migration. And after the gas fades, the surviving planets continue around both stars. What once looked like an unlikely arrangement begins to appear as a natural outcome of repeated physical processes. Not an easy outcome, not an inevitable one, but a path the universe can follow. Somewhere in a young system, two stars are still surrounded by the material that may one day become planets. Dust grains are colliding beyond the cavity. Spiral waves are passing through the gas. Small bodies are growing, breaking, and gathering again. Nothing in that disk knows what shape the final system will take. For now, there is only motion, material, and time. The first circumbinary planets did not announce themselves with a regular beat. A planet around a single star can produce a simple pattern. Each time it passes between that star and Earth, the same fraction of light is blocked. If the orbit remains steady, the dimming returns after nearly the same interval. A telescope records a row of similar events, and the period can be measured by placing one transit over the next. Around two stars, that neat repetition is broken. The planet may return to the same part of its orbit, but the stars will not be where they were before. One may be moving toward the planet's projected path, while the other moves away. A transit can begin early, arrive late, last for several hours, or disappear during an orbit when the geometry no longer produces a crossing at all. The depth changes as well. If the planet passes across the larger star, it may block a measurable amount of light. If it crosses the smaller companion, the event can be shallower or deeper depending on the relative sizes and brightness of the two stars. Sometimes the dimmer star contributes so little to the total light that a planetary transit across it is almost lost. For an automated search designed to find repetition, these signals can look like mistakes. They do not line up at one fixed period. Their shapes vary. They are mixed with the much deeper eclipses created when the stars pass in front of one another. Instrumental noise can imitate a single dip, and ordinary stellar activity can change brightness in ways that complicate the record. The discovery process therefore begins by learning the binary itself. When two stars eclipse, their light curve contains a great deal of information. The depth of each eclipse helps reveal their relative brightness and size. The spacing between eclipses shows the orbital period. Differences in duration and timing can expose an eccentric orbit rather than a circular one. Spectroscopy adds motion. As each star travels toward and away from Earth, its spectral lines shift slightly. From those shifts, astronomers can estimate orbital speeds and determine stellar masses. The eclipses provide the changing silhouettes. The spectra provide the movement along our line of sight. Once the stars are understood, unexplained dimmings can be tested as planetary transits. The test is not a matter of drawing a smooth curve through a few points. The positions of all three bodies must be calculated together. Gravity moves the stars. Gravity moves the planet. Every eclipse and transit occurs within the same connected system. Astronomers often use a photo-dynamical model for this work. The photometric part predicts how much light should be visible as one body crosses another. The dynamical part calculates the orbits through time. The model is adjusted until it can reproduce the stellar eclipses, the planetary transits, their changing durations and their irregular arrival times within a single physical arrangement. This method turns disorder into evidence. A false signal may resemble one transit. It is much harder for noise to imitate several transits across two moving stars at the correct times, while also agreeing with the gravitational behavior of the system. The irregularity that makes these planets difficult to find can make them convincing once the pattern is recognized. Kepler was well suited to this patient kind of work. Rather than moving rapidly from one target to another, the spacecraft watched the same broad field of stars for years. Its long record allowed widely separated events to be compared and gave slow changes in orbital alignment time to appear. Within that field were thousands of eclipsing binaries. Their light curves were already active before any planet entered the picture. Large primary eclipses alternated with smaller secondary eclipses. Star spots rotated in and out of view. Some systems showed variations caused by mass transfer or additional stellar companions. Planetary signals had to be found inside this moving background. In some cases, the first clue was a transit that occurred where no stellar eclipse belonged. In others, a sequence of mismatched events gradually formed a planetary path. Human inspection remained valuable because the eye can notice relationships that a search for strict periodicity may reject. The story of TOI 1338 later showed this again with TESS. Its planetary transits did not arrive at perfectly even intervals. Their durations changed because the star being crossed was itself moving. The signal was first noticed while data from an eclipsing binary were being examined, not because the light curve offered the simple signature expected from a planet around one star. The name assigned to a system can make the discovery sound complete. In reality, confirmation is a long process of removing other explanations. A background eclipsing binary might lie within the same patch of sky. Its changing light could be blended with the target. A faint stellar companion could produce shallow eclipses. Detector behavior might create a repeated artifact. Star spots could distort the shape of an eclipse and shift the measured time. Ground-based telescopes help separate these possibilities. High-resolution images can search for nearby stars. Spectra can reveal whether more than two sets of stellar lines are present. Observations taken months or years apart test whether the same dynamical model continues to predict the system. The planet must survive not only statistical tests, but physical ones. Its proposed orbit must remain stable. Its transits must occur when the model says the planet and star should align. The inferred sizes and masses must be compatible with the observed light and motion. This is one reason circumbinary planets can become unusually well-characterized systems. The eclipsing stars provide strong measurements of one another. Their mutual orbit gives the stellar masses and radii, with a precision that isolated stars often do not allow. When a planet crosses one or both stars, its size can be compared with stellar disks that are already carefully measured. In certain systems, the planet also alters the timing of the stellar eclipses. The effect may be small, but a planet carries mass. As it travels around the binary, all three bodies orbit a shared center of mass. The binary can shift slightly toward and away from Earth, changing the distance its light must cross. Gravitational interactions can also alter the exact timing of the stellar orbit. These eclipse timing variations offer another route to the planet. Transits reveal the silhouette of a world. Timing can reveal its pull. Not every circumbinary planet is aligned to cross its stars from Earth. Most likely are not. The transit method therefore shows only a narrow part of the population, favoring systems whose orbital planes happen to be viewed nearly edge-on. Even among aligned systems, visibility can be temporary. A small tilt between the planetary orbit and the stellar orbit causes the planet's path to precess. Over time, the line traced across the sky shifts. A world that produces transits during one decade may stop in another, then return after the geometry cycles around. The absence of a transit does not always mean the absence of a planet. It may mean the window has closed. Radial velocity searches can reach beyond that window. Instead of waiting for the planet to cross a star, they look for the slow motion of the binary caused by the planet's gravity. The task is demanding because the two stars already produce large velocity changes as they orbit each other. Their motion must be modeled and removed before the smaller planetary signal can be seen. This resembles listening for a low note beneath two louder tones that are constantly shifting. The stronger pattern is not noise, it is the binary itself. Only after its rhythm is known can the additional movement become clear. Microlensing offers a different path. When a foreground system passes close to the line of sight toward a more distant star, its gravity can magnify the background light. A planet around a binary may add a brief feature to that magnification pattern. This method does not require the planet to transit or the host system to be nearby. It can reveal worlds at wider separations and in regions of the galaxy that other surveys do not sample as easily, but a microlensing alignment usually happens once. The event passes and the same geometry cannot be arranged again. Astronomers must extract the system from a temporary brightening whose shape may last days or weeks. Each method sees a different portion of the hidden population. Transits favor large, closely aligned planets with orbits short enough to repeat during an observing campaign. Radial velocity favors planets massive enough to move their host stars. Microlensing can reach farther and detect other separations, but offers only a brief window. Together, they begin to correct the impression created by any one method alone. The known circumbinary planets already show that one architecture does not describe them all. Kepler 34b travels around two stars broadly similar to the Sun, while their own orbit is noticeably elongated. Kepler 35b circles a smaller pair. Kepler 47 contains several planets at different distances, demonstrating that a shared binary can support an organized planetary system rather than a single isolated world. Kepler 1647b follows a much longer orbit than the early discoveries, taking roughly 3 years to circle its two stars. Its transits were separated by such long intervals that the full pattern required the depth of Kepler's archive and careful reconstruction. These systems are not a complete census. They are the systems whose shadows, motions, and alignments became readable from Earth. You can think of the data as a narrow opening through which the architecture passes one piece at a time. A dip in brightness gives a radius. A delayed eclipse gives a gravitational clue. A spectral shift gives a speed. Years of observation bring the pieces into one model. The planet itself remains unresolved, far too distant to appear as a disk. Yet its orbit can be traced, its year can be measured, its place among two moving stars can be known from light that changed by only a small amount before crossing hundreds or thousands of light years. The shadows are brief, but the system they reveal continues long after each transit ends. The light on a circumbinary world would not simply double. Two suns do not act like one brighter lamp fixed in the sky. They move around each other, changing their separation and their position as seen from the planet. Their combined light rises and falls in a pattern shaped by three motions at once: the orbit of the first star, the orbit of the second, and the wider orbit of the planet around them both. At some moments, the stars would appear close together. Their light would come from nearly the same direction, forming two bright disks separated by only a small part of the sky. At other times, the pair would spread apart. One sun might stand higher while the other moved toward the horizon. Their colors could differ as well, especially if one star were hotter and whiter while its companion were cooler and more amber. The view would depend on the system. Some binaries contain stars of nearly equal brightness. Others are dominated by one luminous star and a much fainter companion. Around the second kind, the smaller sun might appear as an intensely bright point moving near the primary. Every star contributes energy. The amount reaching a planet depends on the star's luminosity and its changing distance. Because the stars move within the planet's orbit, the total incoming radiation varies over the binary cycle. Astronomers call this incoming energy stellar flux, or instellation. On Earth, the Sun's output is nearly steady on the timescale of a year, while the tilt of our axis and the shape of our orbit distribute that energy unevenly across seasons. On a circumbinary planet, the familiar causes of seasons could still exist. The planet might have an axial tilt. Its orbit might be somewhat eccentric, but another cycle would be added by the moving stars themselves. It would not necessarily match the planet's year. The binary might complete an orbit in days or weeks, while the planet takes months or years to travel around the pair. The changing light would then pulse through the climate several times during one planetary season. When the stars moved close together from the planet's point of view, their combined illumination could strengthen in one part of the sky. When they separated, one might rise before the other, or set after it. At certain alignments, one star could pass in front of the other, briefly reducing the total light. A stellar eclipse would not bring night. The remaining star would still shine. The planet's atmosphere and surface would also retain heat, but the eclipse could produce a small, temporary decline in incoming energy, repeated each time the stars aligned. Whether the climate noticed would depend on how quickly the planet responded. Rock warms and cools relatively fast. Oceans respond more slowly because water can store a large amount of heat. A deep global ocean could smooth short variations in starlight, holding warmth while the stars changed position and releasing it later. A dry world with little surface water might track the changing radiation more closely. The atmosphere would matter in the same way. A dense atmosphere can move heat through winds and weather systems. Clouds can reflect incoming light, trap outgoing infrared energy, and change where heating occurs. An atmosphere with little mass would offer less buffering. Surface temperatures could rise and fall more sharply as the illumination changed. Climate models suggest that a world rich in ocean could remain surprisingly stable under periodic binary forcing. The sky might change noticeably, while the surface changed only a little. Water, air, soil, and ice would absorb the short pulses and spread their effects over time. The climate would not ignore the stars, but it would answer them slowly. A land-dominated planet could be more reactive. Continents might heat beneath periods of stronger combined light, and cool when the stars moved into less favorable positions. Seasonal winds could be tied not only to latitude and axial tilt, but also to the binary cycle. Storm tracks might strengthen or shift as the atmospheric temperature pattern changed. These are modeled possibilities, not weather reports from an observed surface. No confirmed rocky circumbinary world has yet given us a measured climate. The known systems reveal orbital architecture far more readily than clouds, oceans, or ground. When scientists describe weather beneath two suns, they are testing physical models under plausible conditions, not reading forecasts from a distant planet. That distinction leaves room for many outcomes. Two stars do not automatically make a planet uninhabitable, nor does an orbit within a calculated habitable zone guarantee a living world. A habitable zone is a region where the amount of stellar energy could allow liquid water on the surface of a rocky planet with a suitable atmosphere. It is a useful starting point, but it does not describe the planet's air, pressure, chemistry, magnetic environment, water supply, or geological history. Around a binary, even the starting point is more complex. The stars may have different temperatures, so equal amounts of energy from each do not interact with an atmosphere in exactly the same way. A hotter star emits more of its light at shorter wavelengths. A cooler star contributes more at longer wavelengths. Ice, clouds, gases, and surfaces absorb and reflect those colors differently. The habitable zone must therefore account for more than the total brightness. It must follow the spectral character of both stars, their changing positions, and the stability of the planet's orbit. A region warm enough for surface water is useful only if a planet can remain there for long spans of time. This joins two boundaries that do not always cooperate. The inner stability boundary tells us how close a circumbinary planet can safely travel before the stars disturb its orbit. The habitable zone tells us where a suitable rocky world might receive a favorable range of energy. In some systems, the habitable zone lies comfortably beyond the unstable region. In others, much of it overlaps with dangerous orbital space or falls too close to the binary to support a long-lived planet. The masses, brightness, separation, and eccentricity of the stars decide how these regions fit together. A pair of small, cool stars may provide a habitable zone close to the center, but that zone could approach the instability boundary. Two brighter stars place the habitable region farther out, where the planet's orbit may be safer but its year becomes longer. There is no universal double sun climate. Each system has its own geometry. Consider a planet on a nearly circular orbit with little axial tilt. Around one star, such a world might experience weak seasons. Around a binary, it could still receive repeating variations as the two suns circled within its sky. Now imagine a planet with a tilted axis and an elongated orbit. Its hemispheres would alternate toward and away from the light. Its distance from the binary would change during the year. The stars would continue their shorter cycle inside all of this. The planet's climate would be driven by overlapping rhythms rather than one simple calendar. Some cycles would reinforce one another. A hemisphere's summer might coincide with the planet's closest approach and a phase of stronger combined illumination. At another point in the long-term pattern, the same summer could arrive when the planet was farther away and become milder. Other cycles would interfere. A peak from one rhythm might meet a low point from another. Over years or centuries, the pattern could shift as the orbit slowly precessed. The climate might experience long beats formed by shorter cycles moving in and out of alignment. Earth has its own overlapping astronomical cycles. The shape of our orbit changes, the direction of our axis turns. The tilt varies over long periods. These changes alter how sunlight is distributed and contribute to glacial cycles. A circumbinary world could possess comparable long-term variations, with additional gravitational forcing from the central pair. Its seasons might be perfectly predictable, but prediction would require a more intricate calendar. Predictable does not mean familiar. On the surface, dawn could begin with one star and deepen when the second rose. Shadows might split, with each object casting two outlines in different directions. As the suns moved closer in the sky, the shadows could nearly overlap. As they separated, the ground might carry a pair of distinct dark shapes. Sunset would also change. One star might disappear while the other remained above the horizon, extending the decline of daylight. On another part of the orbit, both could set within minutes of each other. Their order might reverse as their motion around the barycenter changed the sky. The planet's rotation would still set the basic length of day and night. The binary orbit would reshape what happened inside each day. A place near the equator might watch the suns follow related but not identical paths. At high latitudes, one could skim the horizon while the other remained hidden, depending on the planet's tilt and seasons. Polar daylight might contain alternating brightness as the stars shifted around one another without fully setting. Plants, if anything like plants developed there, would face a light cycle unlike Earth's. They might respond to the combined energy, to the color of each star, or to the recurring binary period. Biological clocks could form around several reliable signals: planetary rotation, planetary year, and the shorter dance of the suns. This remains speculation grounded in known physical cycles. Life has not been detected on any circumbinary planet. Even the presence of a rocky surface in a favorable orbit would leave the larger questions unanswered. But the changing light would provide structure. Organisms do not require a simple sky. They require conditions they can survive and patterns evolution can use. Regular variation can become information. Weather and oceans would also respond. Atmospheric tides could follow periodic heating. Ocean currents might carry energy across intervals longer than the binary cycle, while polar ice grew or retreated according to the balance among these influences. From a distance, the planet would not appear confused. Its clouds would follow pressure. Its oceans would follow gravity, wind, and heat. Its seasons would emerge from repeatable motions. The system might be difficult for us to describe because our calendars were formed beneath one sun, but the planet would never need to compare itself with Earth. It would simply receive the light available to it. Two stars would cross its days in a pattern older than any weather on its surface. Their eclipses, separations, and returns would become part of the climate's background rhythm. And beneath those changing suns, even an unfamiliar season could arrive on time. A stable orbit and a moderate amount of starlight are only the beginning. For any planet that might support liquid water, the next questions belong to its atmosphere. Can the air remain in place? Can it move heat from one region to another? Can it protect the surface from the more energetic parts of the star's radiation? And can those conditions persist for long enough that chemistry has time to become complicated? Around two stars, these questions do not have one answer. The character of the system depends strongly on the stars themselves. A pair of small, cool stars creates a different environment from two stars similar to the Sun. A mixed pair with one brighter primary and one faint companion creates something different again. The stars' masses determine their lifetimes. Their temperatures shape the colors of the light. Their ages influence how rapidly they rotate and how active their surfaces remain. Young stars can be restless. Ultraviolet and X-ray radiation can heat the upper atmosphere of a nearby planet, allowing some gases to escape into space. Over long periods, repeated activity may thin an atmosphere or alter its chemistry. A planet around a binary receives these influences from two sources. That does not always mean twice the damage. One star may be much less active than the other. A dense atmosphere can absorb high-energy radiation in its upper layers, and a planetary magnetic field may redirect some charged particles. But two stars create more possibilities. Their magnetic cycles can rise and fall on different schedules. One may be young and active, while the other has already settled into a calmer stage. Their combined radiation may vary over periods longer than the binary orbit, adding another layer to the planet's environmental history. This history matters because habitability is not a snapshot. A world may pass through a favorable temperature range for a few million years and still offer too little time for stable oceans or complex chemistry. Another may remain moderate for billions of years, despite short-term variations, because its stars change slowly and its atmosphere is resilient. The most promising systems would not simply place a planet at the right present distance. They would provide a long interval of orbital stability, manageable radiation, and a climate that does not repeatedly cross destructive thresholds. Stellar evolution sets the outer frame. Sun-like stars brighten gradually as they age. Smaller stars evolve more slowly, though many remain magnetically active during their youth. In a binary, the two stars do not always evolve at the same rate. If their masses differ, the heavier star consumes its core hydrogen faster. It may brighten and leave the main sequence, while its companion remains comparatively unchanged. A planet that once received a balanced amount of energy could later face a very different sky. The system's habitable period may therefore be limited by the faster evolving star. A circumbinary planet also experiences gravitational tides, but not always in the way a world close to one small star would. Tides arise because gravity pulls more strongly on the near side of a planet than on the far side. Around a single star, a very close planet may gradually become tidally locked, turning one hemisphere toward the star and the other away. Circumbinary planets must usually orbit beyond the inner stability boundary. This often places them far enough from the stars that direct tidal locking to the central pair is less likely. The binary can still raise changing tides. As the stars move around their barycenter, the direction and strength of their individual pulls shift slightly. These variations may affect the planet's rotation, its axial tilt, and the behavior of any moons it possesses. A moon could make the picture more intricate. Many known circumbinary planets are giant worlds. If some of them possess large moons, those moons could have solid surfaces even when the planet itself does not. They might receive light from two stars, reflected light from the planet, and heat generated by tides. Yet no exomoon has been securely confirmed around a circumbinary planet. Their existence is plausible, not established. A large moon would also need a stable orbit around its planet, while the planet itself moved through the changing gravity of the binary. The space where a moon can remain bound is limited by the planet's Hill sphere, the region in which the planet's gravity dominates over the star's pull. Near the inner edge of a circumbinary system, this region can be compressed and disturbed. Farther out, a moon has more room. Its survival would depend on its distance from the planet's mass, and the binary's configuration. Even if such a moon remained stable, habitability would require more than a temperate surface. Its atmosphere would need protection. Its orbit around the planet could create regular eclipses. Tidal heating could help maintain internal activity, but too much heating could drive intense volcanism. Too little might allow the interior to cool and geological cycling to slow. Rocky circumbinary planets may exist in large numbers without yet appearing in our catalogues. Transit surveys are biased toward larger worlds. A small planet blocks less light, and around two moving stars its irregular signal is harder to collect. If its orbit precesses out of alignment, only a few transits may ever be visible. The absence of many Earth-sized detections does not show that such planets are rare. It shows that the search formation models offer cautious reasons to expect smaller circumbinary worlds. Disks around binary stars contain solid material. Planetary systems can support more than one orbit. Migration can move bodies into stable regions. None of these processes stops at the size of Neptune. But expectation is not observation. Until more small planets are measured, scientists cannot know how often they form, how much water they retain, or how their atmospheres respond to binary radiation. There is another uncertainty hidden inside the word stable. An orbit can remain gravitationally bound for billions of years, while its climate changes in large ways. The planet's eccentricity may oscillate. Its axial tilt may vary. The stars may brighten. Magnetic activity may decline. Impacts may add or remove atmospheric gases. Habitability is a history assembled from all of these influences. A world could begin frozen and later thaw. Another could begin with oceans and lose them. A thick carbon dioxide atmosphere might warm a cold surface. Clouds might cool a warmer one. Geological activity could recycle gases between the crust and air, helping regulate temperature over long intervals. On Earth, the carbon cycle connects weather, oceans, rock, and the atmosphere. Rain removes carbon dioxide. Chemical reactions store carbon in minerals. Volcanism returns some of it to the air. A comparable cycle could help stabilize a rocky circumbinary planet, though its behavior beneath changing illumination would depend on the planet's geology and water. Plate tectonics is not guaranteed. Neither is a magnetic field. Neither is an ocean. These are possible planetary properties, not automatic features of a favorable orbit. The most careful way to speak about life under two suns is therefore to begin with conditions rather than conclusions. Can a planet remain in a stable path? Can it receive a workable range of energy? Can it keep an atmosphere? Can liquid water persist somewhere near the surface? Can the environment avoid being reset too often by radiation, impacts, or climate extremes? If those answers are favorable, the final question still remains open. Chemistry does not promise biology. Biology does not promise complexity, and complexity does not promise intelligence. Yet none of those steps requires one sun. The basic materials of life as we know it are not tied to a single star sky. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur are made through cosmic processes that operate across the galaxy. Water can form in molecular clouds and planetary disks. Organic molecules appear in meteorites, comets, and interstellar material. A binary system changes the environment in which these ingredients gather. It does not remove the ingredients themselves. This is why circumbinary habitability is studied seriously. Even though direct evidence of life remains absent, the systems test how flexible planetary environments can be. They ask whether stable climates and long-lived atmospheres depend on the simplicity of one star, or whether nature can build durable worlds under more elaborate patterns of gravity and light. The answer will not come from imagining a double sunset. It will come from spectra. When future instruments separate the faint light of smaller circumbinary planets from their stars, atmospheric gases may leave narrow signatures. Water vapor, carbon dioxide, methane, oxygen, and other molecules absorb particular wavelengths. No single gas would prove life. Some can be produced by geology, sunlight, or atmospheric chemistry. The meaning would depend on the full planetary context, temperature, pressure, stellar radiation, surface processes, and the presence of several gases that are difficult to maintain together. Two stars would make that interpretation harder. Their combined spectra would have to be modeled. Their activity would need to be tracked. The planet's changing illumination would affect atmospheric chemistry and the timing of observations. What now appears as a faint transit could one day become a chemical portrait. For the moment, the evidence remains incomplete. We know that planets can orbit two stars. We know that some occupy regions where temperatures may allow liquid water under suitable conditions. We know that binary systems can remain stable for long periods. Beyond that, the possibilities are still waiting for better measurements. Somewhere beyond the reach of present instruments, a small world may be turning beneath two moving lights. Its atmosphere may carry clouds. Its oceans, if it has them, may store the warmth of one stellar alignment and release it during another. The stars would not ask whether the planet was unusual. They would continue around their shared center, while the world answered with climate, chemistry, and time. A catalogue can look complete long before it becomes representative. The first circumbinary planets were found because their orbits happened to cross their stars from our point of view. That geometry gave astronomers a clear signal, but it also selected a particular kind of system. The planets were usually large enough to block measurable light, close enough to transit more than once, and aligned closely with the orbit of the binary. Those discoveries proved that planets could survive around two stars. They did not show how common such planets were, or what most of them were like. To answer those questions, astronomers must account for the worlds that remain unseen. A planet may be present but tilted by only a few degrees, so its path passes above or below both stellar disks. It may orbit too far out to complete more than one circuit during a mission. It may be too small to create a recognizable dip, or its transits may occur only during a temporary interval of alignment that ended before the telescope began watching. The observed population is filtered by every survey's duration, geometry, and sensitivity. This is why occurrence rates are difficult to estimate. Finding 10 planets does not mean that 1 in 10 binaries hosts a planet. Astronomers must calculate how many systems could have revealed a planet of a particular size and period if one had been there. The unseen worlds enter the mathematics as probabilities. For a transiting circumbinary planet, the calculation must include both stars, the planet's tilt, orbital precession, and the length of the observing campaign. A world may have a low chance of being visible at any single moment. Early estimates suggested that large planets on relatively short circumbinary orbits may not be rare. The uncertainty remains broad because the sample is small and the geometry is complex. Still, the known systems do not look like isolated accidents. They look like the visible part of a wider population. One clue comes from how closely their orbital planes tend to match the planes of their host binaries. Many transiting systems are nearly coplanar. Some of this is a discovery bias because planets with large tilts are less likely to cross the stars. But the pattern also agrees with formation inside a shared disk. A disk naturally gives the stars and planets a common reference plane. Later interactions can tilt an orbit, but a well-aligned system carries a memory of its beginning. The planet, the gas, and the binary may all have emerged from the same rotating structure. Another clue lies in the missing inner planets. The known circumbinary worlds do not travel arbitrarily close to their stars. Their orbits gather outside the theoretical instability boundary, often near it, but not within it. This is one of the clearest signs that gravitational selection has shaped the population. The empty region is not simply a place where telescopes failed. It is a place where planets have difficulty remaining. Farther out, the picture is less certain. Transit surveys lose sensitivity as orbital periods grow. A planet taking several years to circle its stars may cross them only once during a mission, and a single event is hard to interpret. Radial velocity surveys open a different window. Instead of waiting for a planetary shadow, they measure the slow movement produced by the planet's gravity. This is demanding around a binary because the stars already generate a much larger velocity pattern. The orbit of the pair must be modeled with care, and the spectral lines of one star must be measured without being confused by the other. The Bebop survey was designed for this task. Its name refers to binaries escorted by orbiting planets. By following selected eclipsing binaries with precise spectrographs, the survey searches for the longer, smaller velocity signal of a planet around the pair. This method began to reveal systems that transit searches alone could not fully describe. In the TOI 1338 system, the TESS had already found an inner transiting planet. Later radial velocity measurements revealed a second world farther out, now also known as Bebop 1c. The outer planet does not need to cross either star to make its presence known. Its mass pulls on the binary, leaving a repeated motion in the spectra. The system became only the second confirmed multi-planet circumbinary system after Kepler 47. More recently, Bebop 3b expanded the sample again. It was discovered through radial velocity observations in a binary system not already known to host a transiting circumbinary planet. The planet is a gas giant on a roughly 550-day orbit, with a path more elongated than those of many of the Kepler discoveries. That one orbit matters because it does not fit the narrowest picture of circumbinary planets. The early transit discoveries encouraged an image of large worlds parked close to the inner stability boundary on nearly circular paths. Bebop 3b shows that planets can also occupy longer and more eccentric orbits that a transit survey might easily miss. A larger sample will almost certainly widen the architecture further. Some systems may hold small inner planets and giant outer companions. Others may contain only distant worlds or strongly tilted orbits shaped by later encounters. There may also be circumbinary planets around stars. Unlike the quiet main sequence pairs that dominate the transit sample, planets have been proposed around binaries containing white dwarfs, pulsars, and other evolved objects. These systems require caution. Changes in eclipse timing can be produced by stellar activity, magnetic cycles, or imperfect models, and some claimed planets have failed later tests. Yet evolved binaries remain important. A planet found there might have survived dramatic changes in the stars, including expansion, mass loss, or close interaction between the stellar companions. In other cases, a planet could form later from material expelled during stellar evolution. Distinguishing survival from second-generation formation would reveal how adaptable planetary systems can be. Is divided not only by size and orbit, but by history. A world around two young stars belongs to the era of formation. A world around a mature pair records billions of years of stability. A world around stellar remnants may carry evidence of survival through transformations that reshaped the entire system. Each discovery tests a different part of the same question. How much change can a planetary orbit endure while remaining a home for one body around two? The answer depends on more than distance. Mass matters, resonance matters, the timing of migration matters, the presence of other planets matters. Even a distant stellar companion can alter the system over long intervals. This is why population studies are valuable. A single planet can be explained by a special history. A pattern across many systems begins to separate common processes from rare outcomes. With enough planets, astronomers can compare the frequency of circumbinary worlds around different kinds of binaries. They can ask whether tightly bound stars suppress planet formation, whether equal mass pairs behave differently from unequal pairs, and whether planets prefer binaries with nearly circular stellar orbits. They can measure how often migration stops near the cavity. They can look for a shortage of very massive planets or an excess of low-density ones. They can test whether multi-planet systems are common or merely difficult to detect. For now, every conclusion carries the weight of small numbers. The sample is growing, but it remains tiny beside the thousands of planets known around single stars. Statistical patterns can shift when only a few new worlds are added. That limitation is not a failure. It is a description of where the science stands. There was a time when no circumbinary planet had been confirmed around an ordinary pair of stars. Then, one system established the possibility. Several more revealed a family. Multiple planets showed that the architecture could become organized. Radial velocity discoveries began to uncover worlds outside the narrow transit window. The field has moved from asking whether these planets exist to asking what their hidden population contains. That change is quiet but important. A planet no longer needs to cast a shadow for us to imagine it as part of the census. Its gravity may be enough. Its effect on eclipse timing may offer a clue. Its distant light may one day be separated from the stars around which it moves. The old navigators of Earth used repeating lights to locate themselves on oceans. Modern observers use repeating shifts in light to locate worlds they cannot see. The instruments are different, but the act has a familiar shape. A pattern becomes a position becomes a path, and a path, measured with care, becomes another world on the map. The map is still sparse. Between its known points are many systems whose planets remain outside every present window. They continue without transits, without names, and without any need to be noticed. Their absence from the catalogue is only an absence from our view. The next circumbinary planet may already be present in an archive. Its star may have dimmed only once. The signal may sit between two stellar eclipses, too shallow to attract attention, and too irregular to map the patterns used in an early search. Years later, a longer record or a better model may return to that small change in light and recognize an orbit that was invisible before. Discovery does not always require a new telescope. Sometimes it requires a new way of reading what a telescope has already seen. The archives of Kepler and TESS contain light curves from large numbers of binary stars. Each record includes the motion of the stars, their eclipses, surface activity, instrumental interruptions, and perhaps the brief passage of a planet. Searching these records is difficult because the expected signal is not evenly spaced. A conventional transit search folds the data at many possible periods, placing one orbit over another until repeated dimmings align. Circumbinary transits refuse to remain in one place when folded this way. The stars move between crossings. A useful search must predict where each star will be when the planet passes through the system. It must allow transit durations to change and accept that some expected events will never occur from Earth's point of view. New algorithms can test these moving geometries more efficiently than earlier searches. They can examine millions of possible paths, looking for a series of dimmings that belong to one physically possible orbit. The goal is not to ask whether the dips repeat perfectly. It is to ask whether their irregularity follows gravity. Human inspection will continue to matter. Circumbinary systems contain features that are easy to misclassify, and an experienced observer may notice a relationship before a general-purpose algorithm does. But future searches will increasingly combine human judgment with automated modeling. Computers can explore an enormous range of orbital arrangements. People can question the assumptions, examine unusual cases, and decide which signals deserve deeper study. But together, they may recover planets that have been hiding in plain data for years. Longer observations will help even more. A distant circumbinary planet may take several years to complete one orbit. A short mission might record a single transit and leave no way to prove that it will return. A longer baseline can catch the second or third event, revealing how the timing changes as the stars move. Observations from different telescopes can also be joined. One instrument may record the first transit. Another may see the next several years later. Ground-based observatories can monitor stellar eclipses between them, improving the model of the binary and narrowing the possible location of the planet. No single telescope has to witness the entire story. The orbit can be assembled across instruments, countries, and generations of observers. This is especially important because some circumbinary planets appear only during temporary transit windows. Their orbital planes precess, causing their shadows to move gradually across the system. A survey that begins too early or too late may see nothing. Continued monitoring can catch the window when it opens. precise radial velocity measurements will reveal another population entirely. These surveys do not depend on planetary shadows. They search for the slower motion of the central binary as an unseen world pulls it around a larger center of mass. The measurement is delicate. The velocities of the stars can change by many kilometers per second during their own orbit, while a planet may add a much smaller signal. Stellar activity can shift spectral lines. Light from the two stars can overlap. Every effect must be separated without erasing the planet along with the noise. New spectrographs are becoming more stable, and analysis methods are improving. With enough observations, they can follow the binary through many cycles and identify the additional movement caused by a distant planet. This method is likely to find worlds on longer orbits, including those whose planes never carry them across either star. Microlensing surveys will explore a more remote population. These surveys watch dense fields of stars and wait for gravity to magnify the light of a background object. When the foreground lens is a binary with a planet, the magnification pattern can contain several overlapping signatures. The geometry may be complicated, but the method can detect systems thousands of light years away. It can reach planets whose host stars are too faint for precise transit or radial velocity work. A microlensing event is temporary. Once the alignment passes, it does not return in the same form. Yet a large survey can observe many such events, building a statistical picture from brief encounters. It may reveal whether circumbinary planets are common in regions of the galaxy far beyond the neighborhood sampled by Kepler. Wide-field space telescopes will make this possible by monitoring large numbers of stars with steady, repeated observations. Their discoveries will not all be circumbinary worlds, but binary lenses and their planets will be part of the population hidden within the data. Finding more planets is only one part of the future. The deeper challenge is learning what they are. For most known circumbinary planets, astronomers can estimate size, mass, orbital period, and the properties of the two stars. These measurements describe architecture, but they do not show weather, clouds, or surface conditions. Atmospheric study requires light from the planet itself, or starlight filtered through its air. During the transit, a small portion of the star's light may pass through the outer layers of a planet's atmosphere. Molecules absorb particular wavelengths, leaving patterns in the spectrum. Around a binary, the interpretation becomes more demanding. The planet may cross one star but not the other. Light from the companion remains in the measurement. The two stellar spectra may overlap, and each star can have spots, flares, and chemical features of its own. A successful atmospheric observation must model the entire system. It must know which star was crossed, how much unblocked light came from the companion, and how the star's activity changed during the event. Only then can the faint atmospheric signal be separated. Large gaseous planets will be the easiest first targets. Their atmospheres extend farther from their centers and block more light. Smaller rocky worlds will require more sensitive instruments and repeated observations. Future observatories dedicated to exoplanet atmospheres may examine suitable circumbinary planets as the catalog grows. Large ground-based telescopes will add high-resolution spectra, using their collecting area to separate narrow molecular features from the light of the stars. Direct imaging presents an even greater challenge. A planet is dim beside one star. Beside two, the unwanted light comes from two changing positions. A coronagraph designed to suppress a single central source must be adapted to a system in which the bright objects move around each other. The planet also lies close to the stars in the sky, even if its physical orbit spans hundreds of millions of miles. From Earth, the whole system may occupy a region smaller than a fraction of a second of arc. Still, the problem is not beyond physical possibility. Advanced coronagraphs, deformable mirrors, and precise models of stellar light can reduce the glare. In the future, space-based interferometers may combine light collected across separated telescopes, achieving the resolution needed to distinguish smaller worlds from complex multiple star systems. A direct image would first appear as little more than a point, yet that point could be separated into wavelengths. Its color could reveal clouds, temperature, atmospheric gases, and perhaps changes as the planet moved through its orbit. Repeated observations might show the binary climate in motion. The planet could brighten and fade as clouds changed. Thermal emission might respond to the varying distance and arrangement of the stars. Spectra taken during different parts of the binary cycle could reveal how an atmosphere reacts to periodic heating. For the first time, two sun weather would move from simulation toward measurement. Before that can happen, astronomers will need nearby targets. Most of the circumbinary planets discovered through transits are too distant for detailed atmospheric study. Surveys of bright, nearby binaries may find better candidates, especially when radial velocity, astrometry, and direct imaging are used together. Astrometry measures the position of a star with great precision. A planet causes its host system to trace a small motion across the sky. Around a binary, the stellar orbit must again be removed, but a distant massive planet may leave a longer displacement around the shared path. Each method contributes a different dimension. Transits give planetary size. Radial velocity provides mass or a lower limit on it. Astrometry reveals the true orientation and mass of an orbit. Spectroscopy tests atmospheric composition. Direct imaging separates planetary light. When these observations are combined, a world that began as an irregular dip can become a physical place with gravity, temperature, air, and seasons. There is a generational quality to this work. One group builds the instrument, another observes the system. Years later, someone re-examines the archive with methods that did not exist when the photons first arrived. The light waits without changing its record. Here, while the stars continue beyond the walls around you, measurements are accumulating from systems whose full architecture may not be understood for decades. A transit recorded tonight may become meaningful only after another crossing arrives years from now. Science can move at the pace of the orbit. It can return, compare, and allow a pattern to develop without forcing an early conclusion. The future catalogue will almost certainly contain arrangements that the first discoveries did not prepare us for. Small rocky worlds may appear. Planets may be found on strongly tilted paths. Distant giants may circle binaries already surrounded by compact inner systems. Some may orbit stars almost identical in mass. Others may receive most of their warmth from one star, while the second contributes little more than a moving light in the sky. The category will become less uniform as it becomes more complete. That is what happens when a new class of worlds moves from rarity toward population. The first examples define the idea. The later ones reveal how many forms the idea can take. For now, the instruments continue to watch. Two stars eclipse. A hidden planet shifts their timing. A faint spectrum carries the chemistries of an atmosphere not yet measured. And somewhere inside a long record of changing light, another world is waiting for its orbit to be recognized. Two stars can share a sky without making it unstable. That may be the simplest lesson these planets offer. Complexity is not the same as disorder. A system can contain several interacting rhythms and still remain balanced for billions of years. The stars move around a common center. The planet moves around them. Its orbit changes slightly under their combined pull, but not without limit. The variations can repeat, settle, and remain bounded. What looks complicated from a distance may be completely ordinary to the world living inside it. This is one of the habits astronomy slowly teaches. Nature does not organize itself according to what feels simple to us. The solar system gave humanity its first model of how planets should behave. One star stood at the center. Worlds traveled around it in broad, separate paths. For centuries, that architecture felt not merely familiar, but universal. Then other systems began to appear. Planets were found close enough to their stars to complete a year in a few days. Giant worlds occupied orbits smaller than Mercury's. Compact systems placed several planets inside a region that would fit comfortably within Earth's path around the Sun. And among them were planets moving around two stars. Each discovery widened the meaning of a planetary system. The word planet no longer describes a body defined by one kind of sky. It describes a world shaped by gravity, formation, chemistry, and time across many possible environments. Some planets circle one star, some belong to two. Others may orbit larger stellar groups, move around stellar remnants, or travel through the galaxy without a permanent sun at all. The universe does not seem committed to one design. Circumbinary planets are especially valuable because they reveal the relationship between order and variation. Their systems are never static. The stars shift, their eclipses come and go. The planet's visible transits may disappear for generations. The climate, if the world has one, may respond to overlapping cycles. Yet the orbit can endure. Stability does not require stillness. It requires that change remain within a structure. Earth follows this same principle, though the pattern is easier to overlook beneath one sun. Our orbit is not perfectly fixed. The moon moves around us while Earth moves around the sun. The planets pull on one another. The direction of Earth's axis turns over long spans. The shape of the orbit varies. The solar system is active at every scale. Its motions are simply familiar enough to feel settled. A circumbinary planet makes the activity more visible. Its sky would display the mechanics of the system each day. The movement of the stars would not be an abstract calculation hidden in a table. It would be light crossing the horizon in changing arrangements. There might be mornings when the suns rose near each other. There might be seasons when one followed the other across the sky with a wide interval between them. At times, one star would pass in front of the other. The brighter disk would narrow, and the total light would fall for a while before returning. Nothing about this would seem theatrical to the planet itself. It would be the ordinary sky. Any ocean there would have formed beneath those cycles. Any atmosphere would have developed under their combined radiation. Any chemistry on the surface would have known no other source of day. Familiarity is always local. From Earth, a double sunset feels like a symbol of distance and strangeness. From a circumbinary world, our single sun might seem incomplete, a solitary light crossing an unusually empty sky. Neither view is more natural. Each is produced by the architecture in which the observer happens to exist. This is why the study of other planets changes more than a catalogue. It changes the range of conditions we are willing to consider ordinary. A planet can form in a disturbed disk. It can migrate toward a dangerous boundary and stop before crossing it. It can remain stable while the stars inside its orbit continue their shorter motion. It can receive changing light without necessarily losing a stable climate. It may even preserve water and atmosphere beneath a sky that earlier generations of astronomers might have considered too complicated for lasting worlds. Much remains unknown. The confirmed population is small. Most known circumbinary planets are large. Their atmospheres have not been mapped in detail, and no surface has been directly seen. No living system has been found beneath two suns. Even the number of small rocky circumbinary planets remains uncertain. Future surveys may show that they are common. They may reveal that only certain binary configurations allow them to form and survive. They may uncover entire families of worlds on distant or inclined orbits that present instruments rarely detect. The next discoveries may support current models. They may also show where those models are incomplete. That uncertainty is not an empty space in the science. It is part of the subject itself. Astronomers work with what the light permits. A transit offers a radius, a spectrum offers motion, an eclipse offers scale. A long absence may reveal precession rather than disappearance. Each measurement is partial, but partial measurements can overlap until the hidden system becomes clear. This is how worlds enter human knowledge, not all at once. First as a small dimming, then as a timing difference, then as an orbit, then as a body with mass, size, temperature, and a place in a larger structure. The process may take years. Sometimes it takes longer than the mission that gathered the original data. A spacecraft can finish its work while the light it recorded continues to produce discoveries in an archive. The planet remains unchanged by our recognition. It traveled around its stars before anyone noticed. It will continue after the models improve, after names change, and after the first interpretations are replaced by better ones. There is a useful humility in that distance. Human beings do not create these worlds by finding them. We only bring their motions into description. The orbit was already there. The double dawn was already happening. The seasons, whatever form they take, were already passing through their cycles. And the two stars were already returning to the same positions again and again, within a pattern old enough to make every human calendar seem brief. From where you are now, the sky may be hidden by a ceiling, a city, weather, or daylight. The systems beyond it continue without needing to be seen. Binary stars move through the galaxy in great numbers. Some are separated by wide distances. Others circle so closely that they complete an orbit in days. Around a portion of them, planets follow broader paths beyond the changing pull of the central pair. Their light crosses interstellar space. Some of it reaches telescopes. Most of it passes Earth without being measured. The galaxy contains more motion than any survey can hold. Still, a few systems have allowed their geometry to align with ours. Their stars eclipse from our viewpoint. Their planets pass through the narrow line between those stars and our instruments. For a few hours, a distant world removes a small amount of light. That absence becomes evidence, and from that evidence, the shape of another sky begins to appear. Two stars move above a planet that has never known a single sun.